Hello everyone. Hello. Can you hear me? Should I speak into this? おはようございます。Thank you everyone for coming to Vue Fes. I'm really honored to be here, and today, I need to my computer for this one. Is the slides up? Okay. So today I'm going to talk about some of the updates in Vue 3.0. So in case you don't know yet, last month at Vue London, we announced that we are already started the development of Vue 3.0. And I have published a post on Medium with some initial details of what we plan to do and what we have already done for 3.0. And today, this is going to be an update about some of the new things we are going to ship in 3.0. So there are a lot of things we need to provide to the users as a framework. So one of the obvious things is to make it fast. So Vue 2 is already pretty fast, but in reality, we can make it even faster. And then we want to make it smaller. Right? Vue is currently around 20 KB gzipped when you ship it in production. But we have found ways to restructure the framework so that you ship even less code. And we want to also make it more maintainable for us. We want to improve our code quality, improve our build infrastructure, to make sure that we can keep maintaining Vue for the long run. And then we want to make it easier to target native. There are currently projects like Native Script Vue and Weeks, which allows you to use Vue syntax to build native mobile applications for iOS and Android. There are a few things that we can do to make it even easier for people to build such tools. And then we want to make your code more maintainable. When you're building Vue applications, we want to provide you with API improvements and new features that enables you to build faster, easier, and more maintainable applications. So next I'm going to be going over these one by one in more details. First, let's make it fast. All right. So in 3.0, we have completely rewritten the virtual DOM implementation. So 3.0 is a ground-up rewrite. However, we're trying our best to maintain backwards compatibility. So the API, most of the API does not change. We are only changing the internal implementation. A lot of these changes will be invisible to the end user, to the developer. It will probably have more impact on library authors. If you are writing a component library with Vue, there will be some changes that you will have to adapt to. But if you are just using other libraries or you're just building the application with Vue and not using some very, very advanced features, then you'll most likely be fine. So after the rewrite of the virtual DOM, we already have a working prototype of Vue 3.0 that has close to feature parity with 2.x. So we've implemented almost all the runtime features of Vue 2.x. The compiler part is not done yet. So mostly I'll be focusing on the parts that we know or that we will be doing. Compare the two to our 2.x implementation. The new virtual DOM has almost up to 100% performance improvements. So it's pretty much like twice as fast. And we also want to leverage new language features in JavaScript. So ES 2015 introduced a new concept of proxies. This is a new language level feature that allows us to intercept all the operations that you perform to an object. So proxy allows us to rewrite our data observation mechanism as well. So one of the things that Vue is known for is that you can simply mutate your data and the Vue will update. And this is something we definitely want to keep. In current Vue 2.x, it is implemented using getters and setters, which is an ES5 feature. So we use object-defined property to convert your data objects into getters and setters in order to intercept your data mutations and to collect dependencies when your component is rendered. So in 3.x, we're going to rewrite the observation mechanism using proxies. So proxies is so powerful that it actually allows us to provide full language coverage for mutation detection. This means some of the current limitations in Vue 2.x will no longer be a thing in 3.0. For example, using proxies, we can detect property addition and deletion. When you add a new property or delete a property on an object, we can detect that. We can detect array index or length mutations. We can also detect and support map, set, weak map, weak set, and even classes. So you can write a class and use it as your data model. And we'll see a demo later. And then, because of the proxies, we also get to provide faster instance property proxying. So in 2.x, when a component is created, we have to proxy a lot of things on the instance. For example, we have to proxy data, props, and computed properties. And for each of these properties, we need to call object-defined property, which is, in fact, a pretty expensive operation. So this is one of the biggest performance overhead in Vue 2.x. So if you have an application with like several thousand component instances, you have a huge application. This cost of repeatedly calling object-defined property is going to take up a lot of time. In 3.0, we're using a proxy. So when your template renders, the context you're referring to is actually a proxy to the actual component instance. And using this proxy, we intercept all the property get and set, and we return appropriate values based on what key you're looking at. So this actually has much better performance than object-defined property, and as a result, we're again able to greatly increase the performance when you create component instances. So that was the runtime. Okay. So in addition to the runtime, we also have a compiler, right? Vue, when you write templates, Vue uses a compiler to compile your templates into JavaScript. And during that compilation, we're actually compiling your templates into so-called render functions. And render function needs to return virtual DOM. This is very similar to what React is doing. When you use React, you're actually compiling JSX into render functions as well. However, because JSX is a superset of JavaScript, it is fully dynamic. A dynamic language like JavaScript is very, very hard to statically analyze. So there are way fewer assumptions you can make about JSX than versus templates. Templates are statically analyzable because although there are more limitations on how you can write a template, it actually makes it very predictable. So the compiler is able to... Okay. So the compiler will be able to make more assumptions and extract more information. The general idea for compiler optimization is try to extract as much information as possible when we are compiling the template. So I will walk through a few examples. So on the left, we have the raw template that we pass to the compiler. And on the right, we have the code that's being generated by the compiler. There are a few things we can do. For example, we can have a fast path for components. We can tell the difference between a component and a native element. And there is another example is children type detection. So if we look at the code on the right, so we see there is a component here. This is uppercase, right? Because it is uppercase, we know it's not an HTML element, so it must be a component. Because it is a component, we can directly generate code that directly creates component vnodes instead of having to first check if it is a component. So we are moving a lot of work from runtime to the compile time. And because you compile before you ship to production, this cost, you're no longer incurring the cost to your user. Your user won't have to pay for the cost. And children type detection means by looking at the template, we are able to tell how many child elements a parent element have. For example, this component has no children. Therefore, in the code we generate, we have this 0 here. This is a number. It's actually a bitwise flag. So we can internally, our runtime is able to see this number and know, okay, this element has no children, so I can skip anything that's related to children for this component. And this div here, it has a single child. It has a span child. So again, we will generate a number here. This number 2 actually represents this element has a single child. So we will use an algorithm specifically for a single child, which is faster than having to compare two arrays of children. And similarly, when you have more than one children, or when you have keyed versus unkeyed children, we will generate different numbers to tell the runtime what kind of children this element has. So the runtime don't have to guess. It already knows what is there. So it can pick the fastest code to execute. By reducing all of these little overhead, and when you have a big application, all these little optimizations add up and results in faster code. Another thing to note here is we are generating something called monomorphic invocations. So monomorphic means, loosely means you are passing very predictable arguments to functions. So when you call this function, it always receives 4 arguments, no matter what you're doing. So this second argument is actually the data, the attributes of your element. So if you don't have any attributes, you will just pass null. If you have attributes, you will pass an object. By always having the same number of arguments, you make internally this function will have less variances, less differences internally. So the JavaScript engine will find it easier to optimize it. So we're making it easier for the engine to do just-in-time optimization, and this also greatly improves performance. So the examples that's following this will just use the normal H here. So if you're not familiar with Vue's render functions, this may look a bit weird to you, but if you have used render functions before, all of this is the code that we generate by compiling these functions, and they're just returning virtual DOM nodes. So we are able to, because we know this parent element here, this is a component, and it's passing down some content. In Vue, the content you put inside a component is called slots. And slots are what you want to give to a child component and let the child component render inside its own template. In 2.x, slots are evaluated in the parent scope and then passed down to the child. So by the time it's passed to the child, the virtual DOM nodes are already created. This causes a child component with slots to always re-render when the parent re-renders. In addition, when the slot content changes, if it depends on a data property and the data changes, it actually first causes the parents to re-render, then it causes the child to re-render. So this is a lot of unnecessary work. So in 3.x, we are generating slots as lazy functions. So if you generate it as a function, it is not called when it's created. Then we pass the function to the child component. The child component calls the function only when necessary. So what this means is the dependency here, this .hello, this dependency, will be registered by the child instead of the parent. So when this .hello changes, the child re-renders, and the parent can stay the same. The parent no longer needs to re-render. And also, when the parent re-renders, the child no longer needs to re-render because the child will know when it should re-render. So the child becomes smarter. So by decoupling the parent and child dependency, we have, when you change data, you incur less rendering work. So this makes the whole application much more efficient on a whole. So this is something that other virtual DOM implementations like React don't really have, because a lot of these code, if you have to write it by hand, it would become very difficult. So because of the developer experience will be bad. However, when you use templates, you will get these optimizations for free. Another example is something called static tree hoisting. So static tree hoisting means we are detecting some parts of the template that is static. It doesn't depend on any data. So the compiler is able to just create the static parts outside of the render function. This is called hoisting. We are lifting the static parts outside and reusing it on every render. So we are just reusing the same static tree every time the component updates. And because it's the exact same tree, when the virtual DOM differ sees that it's the same tree, it will just skip the whole tree. So we're again skipping unnecessary work. This is one of the overhead. What biggest overhead in virtual DOM updating is you have to diff things even if they did not change. But however, if we can detect at compile time that something that will never change, then we will never need to compare them again. So now static tree hoisting has a limitation because the whole tree with nested nodes, nested children, needs to be all static to qualify for static tree hoisting. However, even for some node that contains dynamic content, for example, here we have a div that contains some dynamic text. But the div itself is actually static. It has static ID, static class. There's no dynamic binding on the div itself. So instead of hoisting the whole tree, we hoist its data props. So we can create this static object with ID and class information, put it outside of the render function, and reuse it for the div on every render. So now, again, when we compare this div on a re-render, we see that its data object is exactly the same, so there's no need to diff again. There's no need to compare it. So now we can directly go to its children. So this node becomes pretty much free in component re-renders. And then we have something called inline handler hoisting. So when you write a template like this, you're actually creating an inline function inside the generated code. An inline function, when you pass it down to the child as a prop, it actually will cause the child to always update, because on every render you're generating a different function with a different identity. So we are able, the compiler can actually simplify this for you. So we will just create a constant function, and then we will have a helper method that takes this function and return a bound version that's bound to the instance. And it will always return the same one. After the first call, it will always just return the same function. So this is essentially caching this function for you, so that you're always passing down the same handler on each render, again, preventing unnecessary updates. So we talked about 5 different optimization techniques, right? So each of these, if you are writing raw render functions yourself, would be very, very hard to do. It would make your code unreadable. However, the compiler does not care. So when you write a template, you don't need to think about any of this. The compiler will do all the work for you to generate the most efficient code possible. Okay, so with all these optimizations and the new implementation, the new virtual DOM, new component instance, proxy, all of these combined, we are able to achieve 100% speed increase. So that means almost everything is twice as fast and uses half the memory. So here is a screenshot of some real benchmarks. So this is rendering 3,000 component instances, stateful component instances. So each of these, each component instance has its own state, has some props, and we are rendering 3,000 of them. So as you can see, this is the time spent in pure JavaScript. This is 2.5, and we're spending 280 milliseconds. And with 3.x, we're spending less than half. That's 126 milliseconds. And the memory usage also drops by more than half. So when you upgrade to 3.x, you should see very significant performance improvements. So this will make your applications faster, lighter, and I think this is, and most important, you don't need to change anything in terms of the code you write. You can write your code the same way as before, but magically your application becomes faster. So that's the point of the framework. We are trying to do things under the hood to help you build more efficient applications. So in addition to raw performance, we also care about the size, because when you need to ship code to the user, they need to download the code, and the browser needs to evaluate the JavaScript. So the bigger size your bundle, the more work the browser will need to do. And in order to make your application small, there is a technique called tree shaking. So tree shaking means automatically removing code that isn't used in your application. So for example, when you use a framework like Vue, we are shipping a lot of features, but you don't necessarily use every single feature. Sometimes you may just use maybe half the features, and it would be best if we can remove the code of the features that you did not use. So tree shaking does exactly that. And Vue 3.x is designed with tree shaking in mind. So when you use it with a modern bundler like Webpack or Rollup, both provide tree shaking capabilities, and you will be using a build of Vue that's shipped as the ES module, and you will be importing things on demand. Anything that you did not, a lot of the things that you did not import will then be able to be removed by the bundler when you build for production. Some of the examples, like features like Keep Alive, Transition, vModel, v4, async component, handling async components, mixins, and memoizing. A lot of these features are optional. So if you did not use them, the compiler will not import them, and then it will not be included in the code you ship to your users. So of all the code, if you did not import anything, you just use the most basic features, the new runtime will be around 10 KB gzipped. So that's around half the size of the current runtime. So again, we're cutting everything by half. So time spent by half, memory by half, size by half. And then we want to make the Vue code base itself more maintainable. And to do that, the rewrite actually thinks about a few things. First, we used a cleaner architecture. So the new code base, instead of a single code base, we are actually splitting the framework into multiple packages. For example, we will have the difference between runtime, compiler, observer, and scheduler. They are all decoupled packages and have better test setup. So here I want to quickly do a showcase of the actual code that's work in progress. Oops. So we have this is the current work in progress repository, and as you can see, this is using a monorepo setup. So this is a single repository containing a lot of discrete packages. So we have compiler core, we have the observer. The observer is now an individual package that you can use alone. It has its own API, has its own tests, and even its own documentation. And then we have a runtime core. So the runtime core is platform agnostic. This means it does not depend on any browser features. It is only using pure JavaScript. The logic can run on any platform that supports JavaScript. And then using this runtime core, we can build on top of it to create the runtime DOM, which targets browsers, which uses the DOM APIs. And we also can do runtime test, which is a renderer that actually runs completely in Node.js, so that it makes it easier for you to write tests that doesn't need a browser to run. And we'll show you the custom renderer API that can be used to create that in a moment. And then there's the scheduler. So the scheduler is the part that is responsible for deciding when to do work. So when you change state, the components will need to re-render. A single state change may trigger updates in multiple components. So the scheduler will have to decide which component gets updated first, which component gets updated later. And in Vue 2.x, all of this is really just we're waiting for next tick, then we do everything synchronously. However, by tweaking the scheduler, we will be able to do some more amazing things, which we will show a bit later. So then we'll be server renderer, and you don't need to individually use these packages when you use Vue 3.0. These are all internal packages. So the final Vue package, this is the package you will use, and it's assembled together using these internal packages. So these packages are mostly there to help us make the code itself more maintainable. Okay. So we're talking about making it easier to target native applications, iOS, Android, and we talked a bit about custom renderers. So in 3.0, we are going to provide a dedicated custom renderer API. So what does custom renderer mean? Vue's virtual DOM can work completely in pure JavaScript, so it doesn't need a browser to run. This means we can leverage the Vue runtime to render to different targets. You can render to the browser, DOM. You can render to, for example, Canvas. We can render to iOS. We can render to Android. You can even render to, say, just like log some text to the screen, right? So this is what enables projects like NativeScript and Weeks to build on top of Vue, that allows you to use Vue syntax to build native applications. However, because 2.x did not expose a dedicated API, they had to fork Vue in order to achieve these functionalities. So in 3.x, we're providing a clean and easy to use API for creating custom renderers. And I'm going to do a very quick demo. So the first thing we want to see is this custom renderer. So this is the code that I'm actually using the custom renderer API. So I've created a standalone build of the core runtime. So I'm importing the create renderer API from it. And then what you need to provide to the API is a bunch of functions called node operations. So for example, because eventually when Vue's runtime tries to render to the browser, all it does is just creating and inserting DOM nodes, right? So if you have a div, we need to call document create element to create a div node, then insert it to the document using parent.insert node or insert before, right? So you need to create these corresponding functions and create element, create text, insert before, remove, and a few others. So this is so I've already written this down, but as you can see, the total code is pretty short. It's less than 200 lines of code, and here we are just creating a normal Vue component. So notice all these demos will be just using render functions because 3.0 compiler is not finished yet, so we will have to use raw render function. But here, we write the same component that you would use in a normal Vue application, and then you just render it. And this is what happens when you run it in the browser. Whoops. Okay, let's see. Okay, there you go. So custom render API, open the console. So as you can see, it didn't put anything into the DOM because the custom render API that I just created does not do any real DOM operations. All it does is logging what it did to the console. So you see exactly what it is doing. It's creating the root element, creating the div, creating a span, creating text, then appending. So it's actually telling you all the things it is doing, it should do, right? So to the browser. So if you want to say render to a canvas, you can actually use this to maintain an object graph, and then just render that object graph to the canvas. So a lot of possibilities here, and we in fact are using a lightweight custom renderer to do testing in the code base itself. All right, so let's keep going. So the next one we want to talk about is making your code more maintainable. So we have a few new APIs that Vue 2.x doesn't have. The first one is the exposed reactivity API. That is the observer package that we just saw. So in Vue 2, most of the time, you will have to put data inside a component. However, in Vue 3, the observation system is decoupled from component implementation. It can be used as standalone. And in that, what I mean is, here's a demo. So the observer API, it has something called, a method called observable. So you can give the observable any object and it will become reactive. So once you create an observable, this shared state has become reactive. And if you use shared state inside your component render functions, if you pass it to a component, use it in your template, that counts as well. It actually allows all of these, any component in your application that relies on this shared state will keep track of it. So when you change the state, it can just trigger things to update. So this is very simple shared state, cross-component state management. So if your application is not that big, you don't need to use Vuex. You probably just need this. So here we are just rendering an app with 2 counters. And by going back to the demo, so we're rendering 2 counters, and if we click, as you can see, the count is in the root component, and it's mutating a shared state, and all the component that depends on the shared state is automatically updated. And this is very precise tracking. And then we have something that we need to, a lot of times the difficulty with developing applications is you don't know why things are changing, right? Understanding why your component is re-rendering, is updating, is very important. So in 3.0, we are giving you a new hook, 2 new hooks, one called render tracked, another called render triggered. So what this means is inside the component, here we are having a parent component that is rendering a child component. So parent component has a count property, and it's just updating the count when a button is clicked, and then passes this count to a child component as a prop. The child component has this hook called render triggered. So inside the hook, you can place the debugger. So if we do this, I'm going to go back and show you the reactivity tracking, open console, and if we click the button, the debugger pauses, right here, it shows you the debugger. So if we inspect in the console, let me make this a bit smaller. The event, it actually gives you a lot of information on the exact key that is being mutated, what operation it is, and what new value is, what old value is. So you'll understand what it exactly is causing your component to re-render. And inside the call stack, if you perform proper black boxing, you can use Chrome's settings to black box it. So you can black box, add a pattern, black box Vue.js. This prevents it from it showing up in your stack traces. And now we have a much better stack trace. So render triggered, and you can go directly to the code, to the line of code that actually caused your component to re-render. So this makes your whole data flow much more predictable. Whenever your component updates, you'll be easily able to locate the exact line of code that caused it to re-render. Okay, so now TSX, TypeScript. I don't know how many of you use TypeScript. If you use TypeScript, can you raise your hand? Oh, a lot of you, okay. So Vue 2.x TypeScript support is not very good. So thanks to Katashin and other contributors, we have decent TypeScript support, but not the best. So 3.0, the code itself is actually written in TypeScript. So you will definitely get much better TypeScript support. So, but you don't have to use TypeScript. So, and by that, I'm going to show you. So this is, when you use TypeScript, we actually now support class 8 component API natively. So you no longer need to use a third-party library like Vue class component in order to write a component using a class. So the class looks like this. So you import the component from Vue's runtime, and you can do interface hello props, class hello extends the component, and you can use the assignment syntax. This will become, this is equivalent to returning count 0 in data. And then you can use TSX as well. And TSX also has proper type inference in it. So for example, you can see the count has the inference type number. You can see the props, the text is supposed to be a string. You can also see that when you use the component with a defined props interface, if we skip this, you actually get a warning saying this component requires a prop name text and you didn't provide it. And if you give it a text with, say, a number type, it will actually tell you that this should be a string instead. So this is full TSX support in 3.x. If you want to use TSX, you will get very good type inference experience. Okay, so then we have better warning. So when you trigger, so this is a component. Again, we have root component, child component, and a grandchild component. So 3 nested components. And if we run this code, so open the warning, open the console, and we'll see the new warning. So ignore the first part. That's irrelevant. So as you can see, we get a warning. Unhandled error in render function, and it actually gives you this component, exactly the component where the error was happened, and you see the props right in the warning. And these props are even inspectable, so you can like open this props object and see what's inside. And then you can expand this to see the whole parent chain. So this grandchild is inside a child component, which is inside an app component. So you get a component stack trace as you do in 2.x. And also warnings are available in more places in the application. So previously in 2.x, a lot of warnings don't have the component trace because we don't have that information. In 3.x, we've extended this information to a lot more locations. So you will get a lot of more accurate, more helpful warnings all over the place. And finally, I want to touch upon some experimental stuff that's going on. So some of you may know that React team just shipped a new API called Hooks. In case you didn't know what Hooks is, it's a completely new API that's introduced to make reusing and composing logic easier. So by that, something that's similar in Vue is mixins. How many of you have used mixins? No, not many. So mixins is a way to reuse part of logic in multiple components. You can also use multiple mixins in a single component. So it's very useful. However, it has some problems, especially when you use multiple mixins in the same component. These mixins may come into namespace clashing. So mixin A may inject a property. Mixin B may also inject property. So when you look at the final component, you will not be able to tell which mixin this property comes from, right? So if you have a component with like 5 mixins, it will be very hard to see like what property is corresponding to which mixin, and the logic becomes a lot harder to understand. So Hooks gives you a way to make such logic easier to reuse and more composable. So when you use hooks, the composition is very explicit. So because I don't have enough time to fully explain what hooks is, I recommend those who are interested to watch the talk by Dan Abramov. He recently given at ReactConf to understand what hooks is. But here, what I'm going to do is just to quickly demonstrate that the experimental hook support. It's actually pretty simple to implement. So we have a React compatible basic support for hooks inside both Vue 2 and Vue 3. So hooks have, the two most basic hooks are useState and useEffect. Using those, I was able to create a custom hook called useAPI. And you call hooks directly in your render functions. So I call useAPI with an API endpoint without having to. So if you have done data fetching in Vue before, what you typically do is probably send the HTTP request, send the XML request, AJAX in your component, in your mounted hook, then wait for it to complete, then mutate some data, right? But with custom hooks, none of that is needed. You actually just call useAPI, give it a string, and you get back 3 values: status, data, and error. And depending on the status, you just render different things. So all the logic related to calling HTTP and setting up state, mutating state when things change, or aborting requests is encapsulated cleanly inside this reusable useAPI thing. And in order to use it, all you need to do is just calling this one line of code. So showing you this what this actually looks like in action. So you can see it's fetching some data from a mocking API. Then if we increment the ID, it'll fetch a new user. It'll fetch a new post. So the ID is incrementing. And what's cooler is, like, if I click this repeatedly, as you can see, we are actually making a lot of requests, but we are correctly aborting any request that's out of date. And finally, only displaying the correct result of my last click. So this complicated asynchronous logic is fully encapsulated inside a custom hook, very cleanly. And you can compose this custom hook with other custom hooks. So I think hooks is a very interesting concept. We may eventually we will ship something similar. We may not ship something that's completely the same with React implementation, but I believe it's a good pattern, and we will likely encourage thinking about using hooks instead of mixins when you need to reuse logic across multiple components. And finally, this is something that I was playing with in the past few days. This is something called time slicing. Again, this is something that React team just recently, they had something called concurrent React. The high-level idea is when you have a lot of components. So let's take a look at what we're doing. So this is a basic application. This is a function. Inside this, we are just we're pretending that we have a very, very expensive component, which will take 1 millisecond to render. We'll just this is a while loop, so we're just blocking the whole thread for 1 millisecond for every component. So this is a test component. It will block inside its render function for 1 millisecond, and we are rendering 200 of this component. So every time we render all 200 components, it will take at least 200 milliseconds, right? And then we have an input. So in the demo, we'll see that time slicing off. We have an input box. When we type in this input box, it will update all 200 components at the same time. This is the current behavior of Vue without time slicing. So if I say, so when I type, it waits for 200 milliseconds before it updates, right? A single letter is fine, but what if I type really fast? It's stuck, right? And finally it updates. So this is totally not responsive, right? Because every event is actually received by the browser, and it keeps doing repeated work until finally it finishes all the work. But in fact, because I typed really fast, some of these intermediate state is not even necessary. Like all of these, it didn't need to update at all. You just need to directly jump to the end state. So what time slicing is doing, your code doesn't need to change. You use exactly the same code. The only thing we are using is changing this to a different build of Vue, which includes time slicing. And if we use that instead, completely responsive and only updates when it needs to. So how are we achieving this? So I'd like to use the performance tab to do some profiling. So if we hit record and then we start typing, and then we stop. So let's take a look at the where are the frames? Oh, okay, here. So looking at these, notice how these JavaScript function calls it's not a single long blocking operation. Every operation actually takes around 1 frame, 16 to 17 milliseconds. That's what you need for 60 FPS, completely responsive. And we're actually splitting up work into each frame. And when we are out of the frame budget, we will yield to the browser so that the user input events can come in. And when a new event comes in, it may invalidate some of the existing work. So that means if we type 3 letters really fast, because the second and third events came in before the work for the first letter has finished. So we know that the rest of the first event is completely unnecessary. So we don't need to do it anymore. We just reuse whatever we have already done, and instead just directly jump to update for 2. And then before we finish for 2, 3 comes in. So okay, we skip 2 and just directly do 3. Now, because of this, we get a completely responsive application, even though you're actually doing a lot of work. So this, without any code change, you're actually getting a much more responsive component. This is something experimental, but we have proven that it's possible in Vue 3.0 as well. So that's it all for my talk today. So hopefully this gets you excited about Vue 3.0. And we don't know when we'll ship it yet, but hopefully in mid-2019. Thank you.